At this point, we have a way to compute a 95% confidence interval, where you compute the margin of error as 2 times the standard error. However, that only works for 95% confidence, and we can have other confidence levels. So we have to have a method of getting those confidence intervals, and 2 times the standard error isn't going to work because that's specific to 95% confidence. We're going to run through what we can do so far, and then we'll get to this new methodology for how to handle other confidence levels. Here's a bootstrap distribution based on a built-in sample in StatKey about body temperature, where you have 50 body temperature measurements. So if we were going to compute the 95% confidence interval, we'd need a couple of things. One is the mean of the original sample, x bar, which is right here, the 98.26. Then we need this, the standard deviation of the bootstrap distribution, our estimate of the standard error, which is 0.107, and that's really enough to do it. So from the previous slide, we would have the x bar as 98.26, and then the standard deviation of the bootstrap distribution, which is our estimate of the standard error, is 0.107. So we can substitute in and simplify, and we get our interval, and we can do the interpretation too. These are all things that we could do from section 3.3. Well, what if the confidence level changed? So suppose we want to have a confidence level different than 95%. For the same data, a 99% confidence interval should be wider, a 90% confidence interval should be narrower. The reason for that is that generally if you have a higher confidence level, if you're going to be more confident that you're capturing the parameter, you would need a bigger interval to be more confident. And conversely, if you have a lower confidence level, if you're not going to be quite as confident that you're capturing the parameter, then you don't need an interval that's quite as wide. In general, higher confidence level, you need a wider interval. Lower confidence level, you would need a narrower interval. This slide has the potential to look a little abstract, but it's really not too bad. If your bootstrap distribution looks roughly like that picture, where it's symmetric with a single peak, you can find a confidence interval where the confidence level is different than 95% by using percentiles. Essentially what you do is you have to find the cutoffs so that the central region, which is shaded in red in the picture, matches your confidence level. To be a little more specific, let's say we wanted a 99% confidence interval. So our confidence level is 99%, which means we need that central part, the red part, to contain 99% of the bootstrap statistics in the distribution. If 99% is in the middle, then 1% is left over in the two tails combined. And since this is a symmetric shape, you would need half of that 1% in each tail. And then what percentiles would those be? Well, a percentile is named by the percentage of data below it, which graphically would be to the left. So the lower bound on that central region then would be the half percentile, because that's all that's there, it's just that left tail. The right bound would have 0.5% of the bootstrap statistics above it, but then if 0.5% are above, 99.5% are below. So it's the half percentile and the 99.5 percentile. This is what it looks like in StatKey. You want 99% in the middle, where that's written in decimal form as 0.99. And then if you have 0.99 in the middle, then you'd have half of 1% in each tail, and half of 0.01 is 0.005. And then the endpoints of the interval are the cutoffs of that central region with 0.99 in it. So the 99% confidence interval would be from 97.99 to 98.552. I think it's worth pointing out how to do this in StatKey. So I've got another bootstrap distribution here based on the same original sample. It's slightly different just due to the random generation of the bootstrap samples, but that's okay. The way that you get a confidence interval using percentiles is first you have to select two tail up here. Because when you select two tail, that allows you to specify a central region, which is what we want to do, because then we can specify our confidence level there. The default is 95% confidence. That's what the 0.95 in that central region would signify. That's not what we want. We wanted a 99% confidence interval. So you just have to go down here, click on this, and then you can change it. So written as a proportion, 0.99 for 99% confidence, then OK. And that's it. I'm getting a slightly different confidence interval because my bootstrap distribution is a little bit different than the one that's in the slides. So I'm getting 97.995 to 98.539. But that's really it. That's the entire procedure. It's specify two tail in the upper left of the picture after you've generated the bootstrap distribution, and then you specify your confidence level in the center, and then you get your two endpoints. Here's another example, one that involves categorical data instead of quantitative data. This study was repeated in a bunch of different countries where a bunch of fake lost wallets were planted to see at what rate they'd be returned. And for the study done in Canada, 120 fake lost wallets were planted, 77 of them were returned. So the first thing would be to identify the parameter. It's a proportion. We have categorical data. Generally, that's the way it would go because you can't really have a mean if you don't have numbers to start off with. The population looks like it would be all wallets lost in Canada, and then being returned looks like it would be the specification part. So something like this, the proportion of all wallets lost in Canada that would be returned, that's what our parameter is here. And now if we want to find a 90% confidence interval for P, I've already started. I've got two tails selected right here. So if it's 90% confidence, then a 0.9 needs to go in that central region. If there's 0.9 there, there's 0.1 left over, so half of that, 0.05, ought to be in each tail. And then we get our endpoints of 0.567 and 0.708. Just like with the other example with body temperature, I think it's worth it to go through this in StatKey. So I've got a bootstrap distribution here based on that sample proportion, and then we'll go through the procedure. So select two tail, then it's 90% confidence, so I need to click on this button, change the proportion to 0.90, and there we go. In this case, I happen to get endpoints that match the ones in the slides exactly, which certainly is not what happens every single time, but it looks like that's what's happening here. Of those two general statements, the first one has already come up in this section, where if the confidence level is higher, that would necessitate a wider interval. The reason for that, if you think about the way the intervals are constructed using StatKey, is that if the confidence level is higher, then the middle part needs to be larger. 0.99 larger than 0.95. You have to have more in the center. And if the middle part is larger, then its bounds, so the bounds on the central region or the bounds on that middle part, have to be farther out. And if they're farther out, you get a wider interval. The other general statement that if the sample size is larger, then you'll get a narrower interval, that's because with a larger sample size, there's going to be less variability in the bootstrap distribution. The bootstrap sample means, bootstrap sample proportions, whatever you're dealing with, won't vary as much in an individual sense. So your bootstrap distribution will generally be less spread out. And if that happens, you're going to get a narrower interval. Now we have two ways of finding bootstrap confidence intervals. What I have listed as method 1 will only work for 95% confidence. That's what we were doing in section 3.3, where you can compute the confidence interval as the statistic plus or minus 2 times the standard error. For any other confidence level, you've got to use method 2, but method 2 would also work for 95% confidence. So going back to the body temperature example, that is the default setting. 95% confidence, having the 0.95 in the central part of that distribution. So two tail is selected. You look up here, and then there's the 0.95 right here. If there's 0.95 in the middle, then there's 0.05 left over in the two tails combined. So 0.025 in each tail. We have our endpoints of 98.056 and 98.475. Doing this the percentile way. So down below, that's method 2. Method 1, just like before, 98.26 plus or minus 2 times 0.107. If you look at those endpoints, they're different, but they're not very different, especially in the case of the higher endpoints. The difference is 1/1000th of a degree, which is certainly negligible. And even the lower endpoints, 1/100th of a degree, that's not much either. So either method will give you a functional confidence interval or 95% confidence. But then if you don't have 95% confidence, if you have a different confidence level, you're going to have to use method 2. We haven't run into this problem yet, but there is a shape that you want your bootstrap distribution to have, which is one that's symmetric and has a single peak in the center. If you have a weird looking shape, one that's heavily skewed or if it has multiple peaks. So the idea of being spiky with gaps, which is how the authors of our book talk about it, really the term for that is being multimodal, which just means that there are a bunch of modes, where a mode would be the equivalent of a peak. If that happens, then the methods that we've been using in Chapter 3 can't be used. Here's a distribution where the methods of Chapter 3 will not be appropriate. So the bootstrap methods would not be appropriate here. This has a bunch of peaks. There's a peak. There are some lower peaks. There's a peak. There's a peak. There's a peak. We're getting a whole bunch of peaks here. And this is skewed. Look at where the biggest peak is. The left tail looks like it stretches out farther than the right tail does. So there certainly looks like there's some skewness here as well. So this has all kinds of problems. Both things are being violated. It's not symmetric and it doesn't have a single peak. When that happens, the bootstrap methods are not appropriate. So what we've been doing in Chapter 3 is not what you want to do.